Hello everybody, and welcome to this lecture on computer architecture. Today I want to talk to you about Boolean algebra. Let's see how that works. Let's take a look into more detail what it is all about. First of all, I want to talk to you to say that once again that we can see the computer as something that implements our mathematics, or is it that mathematics is describing our computer? As I have said before, there are two ways of looking at things. Don't forget that mathematics is the thing in your head, and the computer is in reality. The computer exists, and while the mathematics is just something in your head. But today we're going to actually follow the reasoning that the mathematics is the basis for the ideas that we're going to implement with our computer. So the computer implements the ideas of mathematics. So how is this done? Well, we will start now all the way back to the beginning. We will start with Boolean algebra. And Boolean algebra, in fact, is based on the logic of, we could call it Aristotle, because he invented the ideas of categories and the idea of logic itself. Boole just implemented it and made it into a symbolic branch of mathematics. So actually, how does it work? Well, let's take a look and start at the beginning. As we will see, it is based on set theory, or group theory if you want. So group theory, it consists of a set of elements. And while we are talking here about mathematics in general, I can never give you a spoiler alert. This is going to be the set of elements, is going to be the set of possible values of our voltages of input and output of our gates. Because don't forget, the computer will implement this. So when we talk about the set of elements, actually it is about the possible physical values, outputs and inputs of our gates. That has to be set in the beginning. So this set actually has a certain amount of elements. And as we know from binary computing, this amount of elements is just 2. We have 2 values, because that's why it's called binary. And these values we can call anything. And what we will see, we will call them 0 and 1. But up front it has to be said that this is just a name that we're giving to it. It's not zeros and ones. It is just 2 distinct names for 2 distinct elements. We could call it also true or false. Actually, that is what Aristotle did. He called it true and false. But we can also call it, Ajax and Benfica, the 2 greatest football teams in the world. And then we can do operations such as Ajax and Ajax is Ajax, and Ajax or Benfica is Ajax. Well, you get the point. But it's more common in computer science to call it 0 and 1. So 0 and 0 equals 0, and so on. But it's not necessary. The mathematics is general. What is not general is then the implementation in physics. So we have a set, and we can then define inside there the subsets. And in these subsets then, or with these subsets, we can make logic operations. And the mathematics, they like to talk about this more formally in conjunction and disjunction. The operations, the 2 operations that we use. Normally in set theory you only use 1 operation. In this Boolean algebra you use 2 operations that are called AND and OR. And the mathematics talk about conjunction and disjunction. And to write it down we can use these symbols. So this is like the sort of like the intersection symbol, or the logic AND symbol, or what we're going to use in our writing down is this dot. And this should not be confused with a multiplication dot. This is not a multiplication. These are not algebraic operators. These are not multiplying and summing. These are just logic AND and this one logic OR. That is not to be confused, although later we will add to the confusion when we talk about sums of products and products of sums and so on. We will see in a moment, further in later lectures. So we have these 2 operations, AND and OR conjunction and disjunction, or these symbols that we're going to use for these operations. So here is like the union symbol, and here's the logic OR symbol, And this symbol that we're going to use reminds us of a sum, but it isn't. It is just the logic OR operation. And on top of that, on top of these two operations and an OR, we'll also have a unary operation that is just the complement of the set. So if we have a set A, then the complement is not A, and we write this down with a bar. So this is just what we're going to use. Now, let's take a look then at what is the mathematics that is then resulting in the workings of our computer. And this is what we call the Huntington Postulates, which is the basis for all modern computing. So what we have a set S that has a number of elements. In principle can be binary, ternary, whatever. It's a limited set of elements. And of course we already know it, spoiler alert, this is going to be 0 and 1. And we have two operations. The operators are this plus sign and the dot, which represent logic OR and logic AND. So what are the 6 Huntington postulates? First one is that it's closed, meaning that if you take two elements of the set and apply the OR operation, the logic OR operation, then the result is also part of the set. The same with the logic AND. Two elements from the set, and using the AND operation, the result is an element of the set. That's quite obvious and common for set theory. The next one is that it's commutative. So A or B equals B or A. A and B equals B and A. It means you can exchange the operands, or as we will see later in the computer, you can exchange the input at the gates, and the result at the output will be the same. That is because of commutative laws. Then the third postulate is that it's associative, meaning it doesn't matter in which order the operations are executed. So A or B or C equals A or B or C. And the other one, A and B and C equals A and B and C. The fourth postulate is that it's distributive, and that we already know from mathematics. The second one that we have here, seems quite normal from normal algebra. Namely, if we read this as a product and a sum, it would be A times B plus C equals A times B plus A times C. This we know from mathematics. But this is not how we should read it. We should read it as A and B or C equals A and B or A and C. And then this one seems more counterintuitive, namely A or B and C equals A or B and A or C. So this doesn't seem to follow the normal algebraic rules we know from our algebra lectures. But never mind, this is just the Huntington postulates. And we will actually use this later, as we will see in this lecture. Now, the fifth postulate is that the postulate that unit elements exist for both operations. So for the logic OR operations, there exists an element, part of the set, I call this Z, that for every element in the set, every element A, applying the OR operation with Z results in the original A. And now at this moment, specifically at this moment, I call this element 0. I could have called it Ajax, I could have called it blue, I could have called it false, I could have called it anything, but I call this at this moment, I define it as, I use the symbol 0. This is not 1 and 0, but I will actually pronounce it as 0, but it is the logic element of this logic operations of this set, and I now define it, I write it down as 0, and I will pronounce it as 0, although it is not 0. The same with the AND operation. There exists an element in the set that when ANDed with any element of the set, it will result in that original element A. And at this moment I will define this as this symbol, and I will pronounce this as 1, although it's not 1. Much confusion, isn't it? Now, the last one is that an inverse exists. For every element A of the set, there exists an element which I call not A, such that A and not A equals 0, and simultaneously A or not A equals 1. So now let's define some more relations. So we already have here A or 0 equals A and 1 equals A, A and not A equals 0, and A or not A equals 1. Let me put it on the side, and let me show you some more important observations that we're going to use. We're going to slowly build our mathematics on basis of these postulates, and then suddenly we will be programming, actually. So how do we do this? And also later we will see how these operations and or and not, how they are made with transistors. But for the moment we just look at the mathematics. So we already had here A or 0 equals A and 1 equals A and not A equals 0, and A or not A equals 1. These come directly from the postulates. But we can also actually find more interesting relations that are just the result of these original ones. So now I'm going to actually prove then, on basis of the Huntington Postulates, I will actually prove the other ones. And the first one I want to prove is the one that I write here, that A and A equals A. So actually A is with ending, it is absorbing itself, and also A or A equals A. It is absorbing itself. So let me first show this. Let me see if I can get my this is what I want to do exactly. So we have here my nice digitizer. What I want to prove is A and A equals A. How do I do this? Well, first A of A, I can just add 0 to it. A, whatever I have, plus 0 or 0 equals whatever I had. So I can plus 0 here. This is A and A. That, and I still have to put the dot there. This is the same thing. So this 0 actually, let me look here, I can expand and use A and not A. That is 0. So the 0 I will replace with A and not A. So this is A and A or A and not A. And then I will put this A in brackets. That is this, as you know, this distributive law, which I will now apply here. I will put this A outside brackets. This is A and A or not A. And A or not A, as we've seen here, A or not A equals 1. So this is A and 1, and that is of course equals, I should put here equals. And A and 1, of course, as we know, this is A. So now I have proven this one, that A and A equals A. That's nice. So now let me also try to prove that A and 0 is 0. And I will actually make use of this new one that I have just proven. So A and 0, I will prove to you that this is 0. How do we do this? Well, 0 equals 0, where do I have it? 0 equals A and not A. So I will substitute it here. So this is A and not A. And then I will use this law that I can execute the operation in any order I want. So I can put the brackets in a different place. This is A and A. Oh, this is not what I wanted. A and not A. And A, as I've just shown here, equals A. So this is A and not A. And as we know, A and not A actually is 0. So now I have proven here that A and 0 equals 0. So that is this one that I have here. Let's continue. So we still have to prove that, let me see which one I want to do now. I now want to prove that A or A equals A. A or A, actually, well, I can multiply this, that is to say, I can end it with 1. Ending with 1 does nothing with the expression. So this is A or A and 1. But 1 is A or not A, as we know here from the Huntington postulate. So this is A or A and A or not A. Now I will use the funny, what I call always the funny distributive law, that is this one, that if I have this product of two bracketed things that have one thing in common, the A, I can put this outside the brackets. So this is, let me see, where am I? This is, I put this funny thing outside, put the A outside brackets. This is A or A and not A. And A and not A, of course, A and not A is 0. So this is A or 0. And A or 0, as we have already here from the Huntington Postulates, we have it here, this equals A. So I have proven here that A or A equals A, and that had to be proven here. The only thing that is still missing, and let me put it here, I hope I have enough space, is that A or 1 equals, now I want to prove that this is, where do I have it, A or 1 equals 1. How do I do this? Well, I replace this 1 with A or not A, A or not A, 1 equals A or not A, so this is A or not A. And I can put the brackets in a different way, I can execute the operations in a different order, so this is A or not A. And A or A, as I have shown here, A or not A, or as I have shown here just before, I've shown here that A or not A equals A, so this is A or not A, and as we've shown, A or not A, this is the Huntington postulate, A or not A equals 1. So we have shown here, proven here, that A or 1 equals 1. So this set of things are actually quite nice. They will be quite useful, but there are other things which are quite useful and they're a little bit strange. And that is, for instance, I will show this example also, that A or A and B equals A. So it seems that the B is completely disappearing from the expression. So let's see how this works. So I say that A or A and B, actually this is what I can do actually here is that I multiply this A by 1. Multiplying, I will end it by 1. That is allowed because A and 1 equals A, so A equals A and 1 or A and B. And now I can put the A outside brackets, so this is 1 or B, and as we know, 1 or something is just 1. So this is A and 1, and as we know, A and 1 equals A. And that is funny because I had here a B in the expression, and this B no longer exists. A or A and B is simply equal to A. And the same thing applies to when we're using ending and oring, exchanging this. So A or A and B, sorry, A and A or B actually equals A. That is another useful expression that we can use in when we're doing logic. So finally, to conclude this one, I also want to show you that the inverse of A actually equals A, and I'm not going to prove this to you because that is much easier shown by the original Venn diagram, as you can show here. This is my Venn diagram that I made here. It is obvious that if you take the complement of the complement, that you go back to the original A. And that is also something useful, that the inverse of the inverse, or the not A, equals A. Now in the next lecture I will show you some very important rule that you can also prove based on these Huntington postulates and these important observations, and that is that the De Morgan's laws that show that the sum of a product is the product of a sum, or to say actually the sum and products actually are just ors and ands, but I will explain this much better in the next lecture when I will talk about the De Morgan's laws. Thank you for your attention and have a nice day.